Welcome friends, welcome to the lecture of DC biasing circuits. So in this video we are going to understand the different biasing circuits for the bipolar junction transistor. So what are these different bipolar junction transistor circuits and how it can be useful for the biasing the BJT. So first of all, what are the objectives? So these are the basic objectives for the DC biasing circuits. That is, state the purpose of DC biasing circuits. That means what is the main purpose behind the biasing. That is the first that if the transistor is not properly biased, then it should be in the inappropriate regions, and where can a transistor cannot work properly. So that one is the major reason for providing the biasing techniques. Second, we can ensure the things by this DC load line and the given values of VCC and the total collector emitter circuit resistance. So there are several resistances over there that we will see in this video, and for all the different biasing conditions. We are about to define some Q point also, and these are these main types of the biasing circuits, that are base bias, voltage divider bias, emitter bias circuits, collector feedback bias circuits, and emitter feedback bias circuits. So first of all we are going to learn about the load line, that what do we exactly mean by the load line. So for that we will take a circuit, and from that circuit we will be able to understand that what actually we mean by the load line. So in load line there would be a circuit. So the circuit will be like this, and here we can see this circuit. So in this circuit there will be an PN junction diode is attached with resistance and some voltages. Voltages are VCC, resistance is RC. So basically if we want to draw the load line for this circuit, so how we can do, then here there will be some justification, that is IC, that is the current through this particular circuit. So we know that the current will completely dependent on this resistance, that what resistance is there attached with this PN junction diode. So to find out the current, what we will do, that is IC equals to VCC divided by RC. Now this one will be the maximum current throughout this circuit, and here will be the maximum voltage throughout the circuit. That we know that the VCC voltage is applied, but now no other voltages will be there in the circuit. So if we connect both the points on y-axis and x-axis, then we will get a line, and this line is generally called as a DC load line. Here I have written that generic DC load line. So it's okay, we can say that DC load line or generic DC load line. So basically this one will be the DC load line, and this DC load line will ensure that in what region our transistor will work. So there will be, as we know, that there are three regions, that is active region, saturation region, and cutoff region. So all these three regions will define the region of operation for transistor, that in what conditions it will operate in saturation, in what conditions it will operate in active or cutoff. So that I have discussed these things in the introduction to BJT video. So in this thing we have basic idea about this, but now what if there will be a transistor circuit? So let's see these things, that for this transistor circuits what we are doing, that we are basically defining 2 points, same as the previous circuit, and we are finding out the collector current, or we can say the output current and the output voltage or the applied voltage. So basically these two things will decide the Q point, and this Q point will be in which region that we need to discuss. This Q point discussion was also been discussed in the introduction to BJT circuits. So right now we are more oftenly concerned about this Q point stabilization and how a biasing technique will affect the Q point. So here we have seen that there is a circuit, and we are defining the DC load line for the circuit, and how it will be done. Then first of all we need to find out the base voltage. From the base voltage, what we need to do is that we need to find it out the current through the this particular input circuit, and from that circuit we can find it out for this region, that is what kind of current will be there. And for this finding out purpose we will use the KCL or KVL techniques for different voltage and current sources, or what for the branches, what kind of current and what kind of voltage is being circulated from that branch. So basically these are the things. And right now, first of all, if we need to find it out for the input circuit, what we will do, that we are assuming this and as an open circuit, both will have same voltage, input voltage, and for the finding out purpose, what we will do, that is VCC is equals to IB into RB, and hence rest of the story is there. That is the basic KCL technique, and that is only for the input circuits, not for output. For output, what we need to do is that we need to apply the KCL at the output circuits, and this one is the input circuits wherever the supply is given over here. So this is the basic technique to find it out for the transistor, and right now we are just concerned about this particular technique. So first of all, the very first case of the connection, or we can say DC biasing circuit, so this one is called as the base bias circuit. And for the base bias circuit, here we can see that there is only two resistance, and both the resistance will be at the same potential, same voltage potential. So basically we just need to apply the KVL. So how can we apply the KVL? Let's see. So here is some equations are written, that is VCC. So see right now how we can apply the Kirchhoff's law, that is VCC equals to VBE minus ICRC. So this is the basic condition. Pardon me, for IBRB, here there is a mistake, that is IB into RB. So why? Because right now we are concerned about the input circuit. So VCC equals to VBE minus IBRB. So basically it will be like this, and if we apply the values which are provided over here, that is there are some RB values, there will be some RC values, there will be some VCC values, and from these things we can define the IC, and from the same thing that by applying VCC equals to VCE minus ICRC, it will be providing you the VCE voltages over here. Whatever the voltage is across these terminals will be introduced by the collector to emitter voltage. So these are the things, and like this way we can able to find it out the DC load line for the transistor purpose. So this is the basic idea, and this kind of circuit, or we can say the biasing techniques, is called as the base bias technique, or we can say as fixed bias technique. So these are its names. One more example regarding the load line, and this will be the load line that 1, 2 and 5 milliampere respectively. Find the values for VC. How can we define these things? That will be completely dependent on the values which are provided over here. So once we will go through the particular circuits, then after you will able to learn this things, or you can do it your own. So this is the basic idea, and this kind of output characteristics will be achieved at the output terminals. So whenever we apply some input voltages, the output voltages will be like this, and we can see the vast difference between the input and the output terminals, or we can say the input and output waveforms. So this is the basic idea, and this one is shown here, the Q point. Now right now the Q point is showing the region of active of transistor, that is that we know that there will be some saturation region particular over here. See, I am describing these things. This one is called as the saturation, and this one is the cutoff. This one is cutoff, and this one is saturation. So these are the basic ideas about the regions, and at what region your transistor is being operated, that can be seen over here. So this one is the active. I will just write A as an active region. So these are the basic region techniques, and like this way we can identify the region of operation of the transistor. So first of all, we are going to learn about the base bias circuit. This is called as the base bias circuit, and right now we are applying the KVL over here, and it will be introducing the base current. Why? Because if we need to find it out the IC and the VC voltages, what we require, that is that we know that IC is equals to beta into IB. Here beta is the current gained, right? So the beta is basically defined as the IC divided by IB. From that relationship we are defining this thing, and once we apply the input voltage to the circuit, and we will start finding the base current, then it will provide somewhat values like this way, that is IB is equals to VCC minus VB divided by RB. For a silicon type transistor, the VB voltages will be definitely 0.7 volts. So these are the basic techniques. So in this way the base current will be identified, and after this thing, from this base current we can identify the collector current. So for drawing the DC load line, one value should be known. So at least one value is with us right now, but after the further operation, then if we need to find it out the voltage of collector to emitter junction, here is the collector terminal, here is the emitter terminal. So VCE voltages can be defined as VCE equals to VCC minus IC into RC. So these are the equations for the fixed bias, or we can say the base bias condition. Here mark one thing, that sometimes they will provide you the beta equals to DC current gain as an HFE, that is related to H parameters. For the H parameters I will describe one more video also. So basically if they want to try some kind of so beta is also defined as the HFE. So these are the basic terminologies related to base bias. So like this way we can identify the different values of the base bias and the fixed bias circuit. So we are taking one example to solve the particular circuit. So here all the values are given, and from these values what we are finding, that is basically first of all we are going to find the IB current, and the IB current is basically defined as earlier I have told, that IB is equals to VCC minus VBE. For the silicon made transistor, it will be showing the 0.7 volts, and once we put all the values, it will provide you some current, that is mostly of microamperes whenever we talk about the base current. Right now we are putting this value into the IC equals to beta into IB, or we can say the HFE into IB. So if we put these things into the equation, and we can get the collector current, that is of range of milliamperes. And after that we are applying the output voltage, and also the output circuit with the Kirchhoff's law. Then VCE equals to VCC minus IC into RC, and basically the VCE will be defined as the 3.94 volts. So KVL will give you all the techniques or all the derivation techniques, we can say, of the fixed bias circuit, or we can say the transistor biasing techniques. All the techniques can be solved and can be derived with the use of the KVL, and this kind of examples will always be asked in different examinations. So mind well these things, and completely solve it out at your own by taking self assessment. So this is one type of example. Another example is given over here, that construct the DC load line. The circuit will be same, and right now we are considering the DC load line. So for the previous example, see here, that is IC and VCE, both the terminologies are taken here, and we are defining the DC load line for the base bias circuit. So IC current is there, we are putting simple the values, and 4 milliamperes is achieved, and VCE, or we can say VCC, that is the maximum voltage and maximum current throughout the circuit, will be connected together, and it will define you the DC load line. And right now we can see that the particular region of operation is that is an active region. So we can say that the transistor is amplifying right now. So this is one idea. Another circuit, that is base bias. Okay, so these are the basic techniques and characteristics. Fine. So earlier what we have discussed right up till now. So now the third, the second, that is the main part, and this one is the best circuit for all over the electronics applications. Whenever some kind of transistor is applied over there, then basically this circuit will helpful for each and every purpose of the transistor. So this is the technique of voltage divider bias. So in this technique, what we are going to discuss, that there will be 4 different resistors connected with this transistor. There are 2 resistors which are collector resistor, and one is emitter resistor. Another 2 resistors will be there, that is named as R1 and R2, or we can say denoted by R1 and R2. So in this technique, what we are going to do, that we are more oftenly concerned about this resistor and what kind of voltages through this resistor we need to find it out. So this resistor current and the voltages both are the concern items. So what we'll do, that first of all we apply some voltage divider bias. That is a very basic rule, that if we need to find it out the voltages across this particular resistor, then what we will do, that R2 divided by R1 plus R2 multiplied by the total voltage. Right now we are taking the VCC as total voltage. Why? Because both the terminals are connected at the same voltage potential. Fine. So from this technique we will be able to find out the base voltage, and after finding out the base voltage we will definitely arrive to the emitter voltage, that is up till here. Why? Because whenever we apply some kind of output voltages, it will be required, and whatever the voltages will be there will lead us to derive the further equation for the finding out the collector to emitter voltages. So here is VE is equals to VB minus VBE. The voltages between this base to emitter will be what? That is 0.7 volt. If and if only the transistor is made of silicon, then we are finding out the current, that is IE. Now you can see that why we have concern about that VE voltages, that VE will provide you the IE current, and now further we are applying the KVL to the output circuit over here. So what it will provide you, that is VCEQ equals to VCC minus ICQ into RC plus RE. That is the output circuit KVL equation, and it will provide you the current that is already defined, but it will provide you the VCE voltages at the output terminals. So this is the technique, and that's how it can be solved. So taking one more example, so here is the example that all the values are given, and first what we have did, that is we have find out the base voltages, and this base voltages will provide you the emitter voltages. Emitter voltages will provide you the emitter current, and that emitter current will provide you the output voltage, that is VCEQ, or we can say the VC. Whenever we talk about the collector current and VCE, or we can say the collector emitter voltage, this both the quantities are mostly used for the Q point stabilization, or we can say that Q point defining parameters. So they are represented as ICQ and VCQ. So that's why they have written that ICQ and VCQ is there. So ICQ and VCQ values are found out, and it will be helping us to draw a DC load line for this particular circuit. So that's how we can find it out, the total voltage divider bias condition parameters, and so in this way we can be able to find out the VCE and IC. So one more circuit, that is emitter feedback bias, and this emitter feedback bias can be defined by these parameters. And how can these parameters will be achieved? That is by applying the KVL techniques. First we will apply the KVL at the input terminals. What we are doing, that is IB, we are finding out the IB, and from that IB condition we are finding out the collector current, and from that collector current what we are doing, we are finding out the emitter current. This emitter current will help us to find it out the collector emitter voltage, and once we will put all the values in this equation, it will provide you the VC voltages, and IC we have earlier find it out over here. So this is the basic idea about the emitter feedback bias circuits, and just you need to apply the KVL throughout this circuit. For the KVL you need to see the earlier section of this video, so you will get some idea about the KVL techniques, that how can a KVL should be applied to the circuit. So this is the one more kind of emitter feedback bias. This all types of biasing techniques can also be applied to the AC analysis, and more often we have used the CE amplifier configuration. There were three types of amplifier configuration. They are common collector, common emitter, and common base. But the more popular techniques for the amplification purpose is the collector, common emitter amplifier circuit. So basically all the techniques of the biasing are mostly explained with the configuration of CE, or we can say the common emitter circuits. The last but not the least, that is collector feedback bias, and it can be defined as follows. And here we have some twist, that is there are two types of currents, that is IB and IC, but If we consider only the current over here, then it should be taken as IC plus IB as described over here for the VCC. So VCC equals to IC plus IB into RC plus IBRB plus VB, and that will provide you the IB current. This all techniques are just shown you by the arrows, so no need to confuse. Just go through the arrows and you will get the basic ideas that how a KVL should be applied. And from this IB condition, you need to just find out the collector current. For this after this collector current, we are basically concerned about the output voltages, that is collector to emitter voltages, and from that we are finding out this by applying some KVL. We are getting the VCEQ equals to VCC minus beta plus 1 into IB into RC, and it will provide you VCC minus ICQ into RC. From this equation we can say that this whole equation will be represented as ICQ. That is a basic terminology. So these are the techniques, and these are the equations for the collector feedback bias circuits. So this is the idea, and we are taking one example for the collector feedback bias. So all the values are given, all the equations we have with us, and we are just putting out the values, and we are getting this much values for the IB, for the IC, and for the VCE. So, and from this parameters we can also draw the DC load line for this circuit. Mind well one thing, that HFE that is nothing but a beta, that is current gain. Beta equals to IC divided by IB for more definitions. So this is the idea. Now after this, that is one more emitter feedback bias. We can say this one is the improved version of the fixed bias, or we can say the base bias circuit. So in this circuit, what we are doing, that one more a resistor that is provided over here for the emitter terminal, and the whole process is same as that of the previous conditions, that first apply KVL to the input circuits and then apply KVL to the output circuits. Once we will get the IB as an output result of the input circuit by applying KVL, then we will provide this IB values into this equation, that is IC equals to beta into IB, and it will provide you the IC current, and from this equation we can be able to find it out the VC voltages. Here one more thing, that if we need to find out the emitter current, then one can also find it out by using this equation, that is IE equals to beta plus 1 into IB. So from this equation we can find out the emitter current, because we already having some values for the beta. It will not happen that they will not provide you beta, or they will also not provide you any kind of other links to find out the emitter current. So it should not be happened. If it will be happened, then the example will be some kind of mistake. So that is the basic idea, and from this equation we can get the I, and these values will be used for the KVL equation, which will we get at the output circuit. Whenever we apply the KVL at the output circuit, we will get this equation, and we can use these values to find out the collector emitter voltages. So up till now what we have discussed, some basic summary is there. We have discussed about the DC biasing and the DC load line, base bias circuits, voltage divider bias circuits, emitter bias circuits, feedback bias circuits, and in this section collector feedback bias circuits and emitter feedback bias circuits are explained over here. So that's all for this video, and don't forget to subscribe my channel, Electronics Simplified by Kedar Dave. Thank you.